In this video, we're going to look at how to simplify radical expressions. I've done other videos like this before, some using the TI-89 graphing calculator and the traditional approach, which is what I'm going to do here. So here we have the form of the type of radicals you'll be dealing with. Just to review here, the n here, of course, is the index. If it's a 2, it's a square root. If it's a 3, it's a cube root. If it's a 4, it's a fourth root, and so on. Now, if it's a square root, though, generally we don't put anything. It's understood to be a 2. And of course, you have your radical symbol. And then the expression under the radical symbol is the radicand. And then you could have a coefficient in front. And generally, we're going to want this to be in simplest form. So this expression right here, if this is the square root, then we don't want to have any factors for this radicand that are perfect squares. So for example, if you have 50, 50 contains a perfect square. 25 times 2. So we have to take care of business here with this one. Or if it's a cube root, this would not be in simplest form if I have the cube root of 16, because 16 has a perfect cube factor. And there's some properties for radicals that will help you deal with that. So here are the properties of radicals. If you have the nth root of a, b, that's the same thing as the product of those nth roots. So we have the nth root of a, nth root of b. If you have the nth root, again, where n is a positive integer from 2 and on, you can break this down into the nth root of the numerator over the nth root of the denominator. And then this expression over here, the nth root of a to the n, would be the same thing as this expression, or the second one. So you can take a radical and express it as with a fractional exponent. So just in the previous example, then they ask you to simplify something like square root of 50. And what you want to do is find the largest square that's contained as a factor of 50. And this property allows you to break it down, in this case, into the square root of 25 times the square root of 2. And then 25c is a perfect square, and the square root is 5. So that's the simplest form for that one. Or you have a cube root, say 16. Now if that were 17, that would be it. 17 would not have any perfect cubes as factors, but 16 can be written as 8 times 2. And using this property here again, you can break that down into the cube root of 8 and the cube root of 2. And of course, cube root of 8, 2 to the third is 8, so that would be 2 times the cube root of 2. That would be the simplest form of this one. And of course, this one allows you to do something like this. If you have, say, a fifth root of 1 over 32, for example. This property right here allows you to break that down into the cube root, or the fifth root, I should say, of the numerator over the fifth root of the denominator. We don't want a radical in the denominator. We could have a radical in the numerator, that's okay, but not in the denominator. So fifth root of 1 is 1, because 1 to the fifth is 1. And of course 32 is the same thing as 2 to the fifth. So perfect fifth power, 5 into 5 is 1, so this gives me 2. That allows you also, from the last property, if you have the fifth root of x, That allows you to write that as an exponential, x to the 1/5. And we'll be applying these properties in the following problems. Let's do this. So this one we pretty much already did. We want to simplify this. So first we want to find out, if we did this already, are there any perfect squares contained as factors for 50? And again, you can pause the video as we go through and see if you can work this on your own, and start the video again and check yourself. So notice 50 can be written as 25 times 2. Always try to find the largest square that divides 50. Now, if that had been something like 31, instead of what we had say 3 times the square root of 31. 31 doesn't have any perfect squares, that would be your answer. But in this case, using the properties that we just looked at, you can break it down this way. Once you have it factored out in the radicand, you can do this, and of course the square root of 25 is 5, and that's going to multiply the coefficient of 3 also. You get that. So 3 times 5 is 15. Your final answer in simplest form is 15 times the square root of 2. Now you can have a mixture of problems, cube roots, square roots. So in this case, we're adding 2 radicals. And just like when you add monomials or polynomials, you can only add terms that are like. So you can add 3x to 4x, but you can't add, say, 3x and 4y. That just stays the way it is, 3x plus 4y. So here we have a cube root of 16 multiplied by 3, square root of 12 multiplied by 5. So the first thing you want to do is, can we simplify each of these individually? So for the first one, find the if 16 has any cube roots, or any perfect cube powers, I should say, as factors. The second one you find for the largest square that divides into 12, and we get this. 8 times 2 is 16. 8. Here, for the first one, we're looking for cubes, perfect cubes. The second one, we're looking for perfect squares. So 4 is a perfect square. 8 is a perfect cube. So using the properties again of the radicals, we can take the cube root of 8, cube root of 2. Over here, we break this down to the cube root of square root of 4 times the square root of 3. And then we just do the calculations there. So the cube root of 8 is 2. Cube root of 4 is also 2. Or I should say the square root of 4 is 2. And then we just do the multiplications. 3 times 2 is 6. So we had 6, cube root of 2. 2 times 5 is 10. We have 10 square root of 3. If these were both square roots, I could add the 10 and the 6. Or if they were both cube roots, I could add the 10 and the 6 and get 16 times that radical. But a square root and a cube root, that's like an x and a y. They're different. So that would be your final answer. 3 square root. At 3 square root radicals, we want to combine. So again, do with this radical by radical. For 24, we try to find the largest square containing 24. The same thing with 150, and the same thing with 72. And then express it as a product under the radical. There you have it. 24 is 4 times 6. 4 is the largest square contained as a factor of 24. For 150, 25 is the largest square contained as a factor of 150. And for 72, 36 is the largest square. That's a factor of 72. So now we'll take the square root of 4 is 2, so it comes outside. Again here, this breaks down to the square root of 25, and the square root of 6. Square root of 25, that was 5. So that's all I'm doing there. Over here in the next one, square root of 36 is 6, so that comes out, multiplies the whatever coefficient you have there, and then the 2 stays under the radical. And then it's just a matter of adding these up, multiplying these and adding them up. So 3 times 2 is 6. 7 times minus 7 is minus 35. 3 times 6 is 18. So now we have all square roots, but they have to be like. Square root of 6 on the first one, okay. Square root of 6 on the second one, but the third one is the square root of 2, not 6. So the third one is different. I can combine these two, but not this one. So 6 radical 6 minus 35 radical 6 is minus 29 radical 6. And then the 18 radical 2 stays. That's your final answer. So here we have a radical expression where we have a radical in the denominator. So your final answer can have a radical in the numerator, but not the denominator. So somehow we have to make this radicand 11 into a perfect square. So we can do that by multiplying the numerator and the denominator by the square root of 11. So that gives me 7 times the square root of 11, and over here, square root of 11 times the square root of 11. That's going to be a perfect square. So it's going to be 121. You can take the square root of that, and you get 11. Square root of 121 is 11. That's your final answer. So this one I have 5 over the cube root of 7. So the numerator is pretty much in simplified form. The denominator looks to be in simplified form. The only problem we have here is it's in the denominator. So just like the first one, in order to fix it, we need to make this radicand here, the 7 under the cube root, a perfect cube. Over here was a perfect square. So what can we multiply in order to make it a perfect cube? Well, we can multiply the numerator and the denominator, and this should be a 5 here. Okay, that should be a 5. So notice I multiplied by the cube root of 7 squared, because in that this will give me a 1 and a 1 there. So when I multiply these radicands out, it gives me 7 to the third, which is a perfect cube. And the cube root of 7 to the third is going to be 7. Okay. Again, this is a 5. And it goes here. So this comes down to the cube root of, again, so your final answer is 5 times the cube root of 7 squared, or you can write that as 49 over 7. Okay, the next one I clicked a couple of times. I gave you the answer here, but so here we're multiplying. So here we're just using the more reliable formula, basic algebra, that if you have the difference and the sum of the same two terms, it's the square of the first one minus the square of the second one. So that's going to be a squared minus b squared. And that works out nicely here because we're dealing with radicals. So when I square radical 13, it gives me 13. When I square 2, it gives me 4. And it's a minus, and 13 minus 4 gives me 9. That's how we get the answer to that. Okay, the next one is kind of similar. And again, to make this into a expression without a radical, I multiplied again using that same formula from basic algebra, multiplied by what is called the conjugate of this. So radical 13 minus 2 multiplied by radical 13 plus 2. So we have the difference and the sum of the same two terms. So I've got to multiply the numerator also by that. So when I multiply these two again, just like in the previous problem, it squares the first one, gives me 13. minus the square of the second one, that's 4. So 13 minus 4 gives me 9. And then, of course, this one I can just leave it as a product. So what I did here is we divided the factor of 6 here and the denominator, a common factor of 3 divided by 3 here. I got 3. Divide 6 by 3, you get 2. So the reduced answer is right here. Now for this one we have 4, the cube root of 16, x to the 9th, y to the 8th, z to the 10th. So again, this is a cube root. So what we want to do is make sure that the radicand has no perfect cubes as factors. So what I did here is I broke this down and said 16 is 8 times 2. Of course, 8 is a perfect cube. It's 2 to the 3rd. 9 is a perfect cube because 3 divides it. Then 8 is not a perfect cube, but it has a perfect cube factor. I wrote y to the 8th as y. Notice the 3 goes into the 6. So that tells me that y to the 6 is a perfect cube. Z to the 10th, 3 doesn't go into 10 evenly. So I know that z to the 10th is not a perfect cube. But it does contain a perfect cube factor of z to the 9th. So broke down z to the 10th as z to the 9th and z to the 1st. So all the ones that are divisible, all the powers that are divisible by 3 are perfect cubes. Obviously 8 is 2 to the 3. So 3 does go into 3. I already said 8 is a perfect cube anyway. So 3 goes into 9, it goes into 6, goes into this 9 over here. So those will come out of the radical. The 2, the y squared, and the z will stay. Those are not perfect cubes. Okay, so here I just did cube root of 8 is 2. I brought it out here. 3 into 9 is 3, so it becomes the cube root of x to the 9th is x to the 3rd. 3 into 6 is 2. The cube root of y to the 6th is y squared, that's out of here. Z to the 9th, 3 goes into 9 again, 3. Cube root of z to the 9th is z to the 3rd. And the 2, like I said, the y squared and the z stay into the radical. And then we just multiply the 2 and the 4 to get the 8. And then we just bring down the other ones, x to the 3rd, y squared, z to the 3rd, and the 2, y squared, and the z stay under the radical. Thanks for watching. We'll see you next time.